Welcome back, everybody. Hope everybody has adjusted to the time change, especially those of you who are not in the United States. Hopefully the time change did not take you by surprise. So today we're going to be continuing to talk about some structures in Java that are useful for storing information. We've encountered a couple of these already in earlier examples and earlier lectures. In several examples we've seen so far, we've talked about the ArrayList class. The ArrayList is a very handy replacement for ordinary arrays, and it's especially handy in situations where you have to store a collection of objects. Also, in the example that I showed on Friday of last week, I showed an example of an algorithm that makes use of another structure to store information, and that is a stack. In the calculator example, we talked about how the algorithm for evaluating arithmetic expressions makes use of a couple of stacks, one to store values and the other to store operators. Right now, both the ArrayList class and the stack class are examples of a broader set of classes in Java, and these sets together make up what are known as the Java collection classes. And in today's lecture, I want to tell you a little bit more about the Java collection classes and introduce you to two more members of that particular set of important classes. Right now, before I sort of dive into the details of those two new classes, one thing that I want to spend a few minutes talking about is the official documentation for many of these classes. We haven't been making much use of this so far in this course, but one feature that appears on the home page of the course website is in the bottom right-hand corner, there is a link to documentation about the Java class library. So let's go ahead and click on that link and see what information is available there. Right, so this is the official documentation for classes in Java. And because there are a very large number of classes available in Java, there's a pretty elaborate system of documentation for all of these classes. And there's also a system of organization that the documentation uses. Right, so the first thing you need to know about is precisely because there are so many classes in the Java class library, the class library uses a hierarchical system of organization. The first aspect of that system of organization is that classes are divided into very large groups called modules. Now, in this course, we're only going to be working with one module, and that's known as the base module in Java. In fact, the link from the course website will take you directly to the page that has documentation about that particular module. There are other modules available in the class library. We will use some members of some of those other modules in Computer Science 250, but in this course, we're only going to be using classes that come from this so-called base module. Then the next level of organization is that within any given module, the classes are further subdivided into packages. So here, for example, when you come to the documentation page for the base module, what you're going to see is a great big long list of different packages that appear within the base module. And again, these packages are organized thematically. They're basically based on different application areas. Each unique application area has its own package and set of classes associated with that application area. Right now, today, we're interested in the so-called collection classes, and the collection classes live in the java.util package, which is one of many packages that is available in the base module. So let's click on the link for java.util, which will take us to the documentation page for this particular package. All right, now the next thing you'll see when you come to a package is that packages typically consist of a large number of classes that sort of have something in common. Most of the classes in the java.util package are what are known as collection classes. They're basically used to represent structures that can be used to store collections of things. Right now, one of these we've met already. This is the ArrayList class. And when you click the link for the ArrayList class, that will take you to the specific documentation page for that particular class. Right? And each individual class's documentation page is organized in the same way. The first thing you'll see at the top of the documentation page for a particular class is some text that sort of gives you a broad overview of what this particular class is meant to do and what its purpose is. There may be short snippets of code or other examples of how to use that class here at the top of the documentation. Now, the most important thing going on in the documentation here is basically documentation on the individual methods that make up a class. Really what determines the functionality of any given class is the set of methods that it offers to do things, and this will be, of course, the most important part of the documentation that you look at for any given class that you're interested in, because the list of methods basically defines what this class is capable of doing and various operations it can carry out for you. Right, so for example, in the ArrayList class, we've already met a number of these methods and talked about how you can use them. Some examples include the add method, which is used to add a new item to the end of the list. There's also the get method that allows you to access items in an array list based on an index system. So if you know the location of an object you're looking for, you can pass in the index to the get method and it will return that object to you. Another example of a method that we've used is the isEmpty method, which will tell us whether or not the list is empty. Right, and over and above those methods that we have used already, most of these classes also offer a very wide range of methods for doing just about every conceivable operation that you can think of with a given class. Here's some examples of methods that we haven't used so far in the array class. For example, the array class has a couple of remove methods. One of these will allow you to remove an item based on an index. You basically specify the location in the list where you would like to remove an item. And what this method will then do is remove that item from the list. And if there are any items after it in the list, it will move all of those one space to the left to fill in the gap that was created by removing that item. You can also remove an item basically by specifying which object you would like to remove. Right, so if there's a collection of objects stored in an array list and you know you have a reference to an object that you know is in the list somewhere and you would simply like to remove it, you can simply pass that object to the remove method and it will locate the object in the list and remove it for you. That saves you from having to actually search for the object and find its index. Another example of a useful method is a method for searching for particular objects. So there's a method here called contains, and the way it works is you pass it a reference to an object and it will search through the array list and it will tell you either yes or no, either yes, the array list contains this object, or no, it does not. Okay, so that's one reason why it's a good idea to basically take a look at the documentation for any of these classes, because in most cases, if there's some operation that you imagine doing with one of these standard classes, it's quite likely that there will be a method available to help you do that operation. And coming to the documentation page on a particular class is a good way to discover whether or not that method that you would like to use is actually available. Right, so that is the ArrayList class, a class that we've already done quite a bit of work with, and this is the documentation page for that class in the Java class library. Right, now, what we're going to be doing today is I'm going to be introducing you to a couple of other classes which are also available in this same set of collection classes. In a few minutes, we'll come back and look at the documentation for a couple of these. But first, let me switch over to my lecture notes for today and begin to introduce you to a couple of other of these collection classes that we'll be studying in today's lecture. All right, the first new class that we're going to study today is a thing called the tree set class. And the TreeSet class is an example of what the Java class library calls a set class. Okay, now a set is a concept that many of you may have encountered, for example, in a math course. In a math course, a set is basically a collection of elements. And some operations you can do with sets include adding new items to a set, removing existing items, and searching for items in a set. And that's primarily what a set is meant to do in Java. It basically represents an abstract collection of a bunch of elements. And the three most important methods that a Java set class offers you are these three methods here. First of all, there's an add method. This is used to add new items to an existing set. Now, the one thing that's a little bit unusual about this add method is that it returns a Boolean. And the reason it does that is that the set in Java has an important restriction. And that is, in a Java set, you can only have one example of each item. So for example, if you've made a set of integers and you've put a number of integers into the set already, one thing that a set will not allow you to do is it will not allow you to put duplicates into a set. So for example, if you have a set of integers and you've already put some numbers in the set, and then you come along with the add method and try to add a new item to the set, if that item would represent a duplicate, that add operation is going to fail. Right? So to help you know whether or not the add operation succeeded or failed, the add method is going to return a Boolean. It's going to return true if you were successful in adding the item to the set, and it's going to return false if you were unable to add the item, presumably because this thing is a duplicate. There's an item like it already in the set, and when you go to try to add a second copy of that item, it will fail, and the add method will return false to let you know that that item was not added. All right, then another obvious method to have in a set class is to have something like a contains method. You can hand it an element and ask, does the set contain this particular item? And it will return either true or false to tell you that. All right, and finally, a third useful method in a set class would be a remove method. This would allow you to take an item which presumably is an existing item in the set and say to the set, we'd like to remove this item from the set. We would no longer like it there. Okay, now, at least as far as these three methods go, there's really not much difference between the set and these three methods and an array list, right? Because for example, it turns out that the array list class contains exactly the same three methods, and an array list is another way to store a collection of items and give you the ability to add items to it, search for existing items, and then remove items. These are all operations that array lists can do already, right? So that leads to the natural question, and that is, why do we need another class that does exactly the same things that an array list can do already? What's the motivation for introducing a completely new class when an array list can already do all three of these things? Right. Well, the actual motivation for introducing a new class in this case is that although the set class offers all three of these operations, its great advantage over the array list class is that the set class is designed to do these operations much more efficiently than the array list class typically can do. Perhaps the prime example of this here is the contains method. If you're using an array list and you call its contains method to ask it whether or not it has a particular element, the array list really has no choice but to just simply do a loop that goes across all of the elements in the list until either it finds the element and can say yes, or it makes it all the way to the end and is able to finally say, no, this element was not in the array list. Right now, so when it comes to the contains method in the array list, that is considered to be relatively inefficient. The array list class is really not the ideal class for doing something like the contains method. Now, the set class, on the other hand, is actually engineered from the ground up to do the contains method very efficiently. Right, and in the next slide, I'm going to show you a little bit sort of an inside view of what actually goes on in a Java set class. and how the Java set class manages to answer the contains question much more quickly and much more efficiently than an array list would be able to answer the same question. Okay, so here's a sort of an inside view of what goes on in a typical Java set class. It turns out that internally, a Java tree set uses a special structure. It's a very commonly used structure in computer science. It's called a tree structure. And what we see here in this slide is 3 different examples of tree structures. Right now, what tree structures are designed to do is they're designed to store a collection of data items, but when you put the items in the structure will organize these items in a special way. And this organization scheme that the tree uses, in turn, makes it much faster and more efficient to search for things. Right, so here are 3 different examples of trees that are specifically organized to make it easy to search for things. All right, so first of all, a tree structure in computer science is a structure that's made up of a collection of nodes that are linked together. And there's a set of terminology that goes with this structure. First of all, the node that sits at the very top of the structure is what's known as the root node. Now, the next thing you'll notice is that in many cases, nodes are linked to other nodes, and we call this set of links in a tree, we refer to these as parent-child relations. So for example, in this tree here, the root node has 2 children, the children that appear to the lower left and to the lower right of that particular node. And as you get further down in the tree structure, there are more instances of nodes that have children connected to them. Right now, in addition to the parent-child structure, the other thing going on within one of these tree structures is that the data stored in each one of the nodes are organized in a specific way. And again, the example all the way to the right is the best example to see this relationship here. In one of these so-called search trees that we're looking at here, the data elements of the children actually bear a special relationship to the data elements of their parents. And here's how the relationship works. When you go to a parent node and compare its data value with the values of its children, what you're going to see is that the so-called left child of a given parent always has a value which is less than the value of the parent. And then at the same time, the right child of that parent will always have a value which is larger than the value of that parent. And that relationship holds for every single node in the structure that has children. In every case where there's a node with children, the left child always has a value less than the parent, and the right child always has a value greater than a parent. Right now, it's that relationship that makes this structure ideal for doing things like searching for things. For example, here is a structure that has a total of 8 elements in it. And suppose we ask a question, for example, does this structure contain the item 20? Right? The way that you would answer that question is you would start at the root and you would make use of these relationships to help you very quickly zero in on the spot where that item might be. Right? So for example, if you're searching for 20 and you come to the root and you see a 13, one thing you know is that all of the elements that are greater than 13 will be found off to the right, right? So that means you should continue your search by going to the right child and ignoring everything that might appear to the left of that 13. All right, so now on the next node you come to, if you see a 25 and you're looking for a 20, you know that all of the numbers that are less than 25 will appear somewhere down to the left. So you'll continue your search down to the left. And in this case, after looking at just 2 nodes, we will land very quickly on the thing that we're searching for. All right, and because the search tree has this sort of organizational principle that it uses at every point in the tree, that makes it extremely fast and efficient to search for things. All right, and that the efficiency of that search gets better and better as the tree structure gets larger and larger. Right, so even in applications where you may have a very large number of items in a tree, for example, 1,000 items stored in a tree, if you go searching for a particular item, it will take you relatively few steps to either find the location where the item is stored or determine that the item is simply not in the collection. Right? And again, to give you a sense of how efficient this is, if we made one of these tree structures and we put 1,000 items in it, and we did a search for any given item, that search would only need to look at about 10 or 12 items before either finding the thing it's looking for or determining that the thing is not there in that list of 1,000 items. Right? And doing a search for an item that takes only 10 or 12 steps in a collection of 1,000 items, that's vastly faster and more efficient than doing something like searching in an array list. Because if you have an array list with 1,000 items and you go searching for an item that isn't there, it will take you 1,000 steps to determine that that item is not there. If instead, if you store your data in one of these tree structures and you go searching for an item that isn't there, it again will only take you about 10 or 12 steps to discover that the item that you're looking for simply isn't there. And 10 or 12 steps is vastly more efficient than 1,000 steps to answer that question. Right, so this is the main selling point in a so-called tree structure. Tree structures are organized to make searches much, much faster. And that is the main selling point in the Java tree set class, because a Java tree set will use something like this tree structure to organize the data items. It organizes them in a special way that makes it very fast and efficient to answer questions about whether or not this collection contains a particular item. Right now, a further side effect of this very efficient search is it turns out that the other two operations here, the adding operation and the removing operation, can also be implemented very efficiently in a tree structure. Right, so that is the main selling point of tree structures, is that they make it very fast to search for things. They also make it very fast to add new items, and they also make it very fast to remove existing items. Those are the three main applications that tree sets are ideally set up to do. Okay, so especially if you are working on a problem where you frequently need to search for things and determine whether or not they are in some collection, the tree set class is the ideal class to use for a situation like that. Okay, now, having said that, at the same time that the tree set class is also very good at doing these operations, there are some other examples of operations that, for example, an array list does particularly well that you may wonder whether or not a tree set can do these operations as well. Here's another example. An example of something that a tree set, that an array list makes it really easy to do, is writing a loop that visits each item in the array list. And this is very easy to do because the ArrayList class has two helpful methods. First of all, it has a size method, will tell you how many items are in the array list. And the ArrayList class also has a get method that will allow you to use an index to access individual items in an array list. And by using both the size method and the get method, you can easily write something like a for loop that is designed to visit every element in an array list and visit those things in some systematic way to do some job. Okay, now a natural question to ask is, when you switch to a different arrangement like this tree set arrangement, is there an easy way to do something like a loop that is designed to visit each element in the set? If you want to, say, for example, print all of the elements in some collection or do some other task that requires the use of a loop. Right, well, first of all, a bit of bad news. The bad news here is that unlike the array list, which has a get method that allows you to access individual items based on an index, the tree set class does not have a get method. Right, and the reason for that is that in an array list, things are already organized in sort of a linear list, and using an index as a way to access items in a linear list is a perfectly logical thing to do. However, in the case of a tree set, these data items are not organized in a linear list. They're instead organized in a non-linear structure. They're organized in a tree structure. That makes it sort of difficult to imagine using something like an indexing system to refer to the individual items. Right, so that's why the tree set class does not have a get method that allows you to use an index to say, okay, let's visit, for example, item number 17 in this collection. Right, well, to replace that, what the tree set offers instead is a couple of alternative methods for doing something like writing a loop and filling up that loop and then iterating over it in some way. Right. The next slide here is going to show you one of these alternative techniques that you can use to write something like a loop that is designed to visit each item in a set. Okay, so what's going on in this example is we're creating a tree set that's going to be storing a collection of integers. And we're going to start out by using the add method to simply add a bunch of integers to our tree set. Right? We have a loop here. It's going to go around 100 times, and we're going to basically add 100 random integers to our tree set. All right, and again, the tree set offers an add method for this purpose. Anytime you want to add a new element to a tree set, you simply call the add method to add new items. Right now, suppose you have added these items to the tree set and you would then want to get a list of all the items that you've added to the set. For that, you would like to be able to visit each item in the set and then print them. Right. Well, to help you do that, that task of visiting each item in computer science is commonly referred to as an iteration task. And to help you do that task, the tree set offers a special mechanism called an iterator mechanism. All right, and here's how this mechanism works. It begins by calling a special method in the tree set class. The tree set has a special method called the iterator method. When you call this method, it will return a special object to you called an iterator object. Right now, as the name suggests, the purpose of the iterator object is it's there to help you do what's called an iteration, which allows you to visit each item in some collection. Right? And here's the code to demonstrate how you typically would use an iterator. First of all, iterators all have has-next methods, which are basically used to determine whether or not the iteration has finished or not. And you'll use that has-next method in combination with a while loop to set up something that says, okay, as long as there are more items still available in the collection, let's go to the next available item. All right, and then the act of going to the next available item, that's done by a second method in the iterator class. It's called the next method. And when you call the next method, it will simply hand you the next available item from whatever collection you're currently working with. All right, in this case, the collection is a collection of integers. And when we call the next method, it will simply give us the next available integer in the set that we're working with. Right? And then that, for example, will allow us to print these individual items. And then so by setting up this loop that goes over each item in the collection, we can then iterate over or visit systematically every single item within that set. Right? So that, in the case of the tree set, that is the replacement for the get method, which would allow you to write a loop that visits every item in an array list. What we do instead with the set is we use an iterator. We ask the set to give us an iterator, and then using the iterator, we set up a loop that visits each item in the set and then allows us to do something with each individual item. Okay, now there's also a second mechanism that allows you to do the same thing, and this second mechanism is even more convenient. All right, so here's another slide that shows the same example, but this time using a slightly different approach to visiting each item in a collection. And this alternative approach, which turns out can be used with any one of the Java collection classes, is to use a special construct called an enhanced for loop. This is a new type of for loop that we haven't encountered before, but this is a type of for loop that people typically use with any one of the Java collection classes. You can use it with an array list, you can use it with a tree set. In fact, you can use it with any of the classes that we're going to be talking about today. All right, and the way this array list, this enhanced for loop works is it has to be used with some sort of a collection, right? So in this example, the collection, once again, is this tree set T that I set up and filled with a bunch of numbers. right? So the T appears here. And then the other thing that you need in the enhanced for loop is you're going to need a variable which will be used to temporarily store each one of the items in that collection. All right, so the way you would then read this for loop is you would read the for loop as saying, for each integer n stored in this collection T, I would like to do something. In this case, again, I would like to print the numbers. So in this case, for each integer n in the set, I'm going to say, let's go ahead and print that integer. All right, so once you get used to the syntax of the enhanced for loop, this is a very simple and easy to use method for iterating over collections. And again, this will work with any one of the collection classes in Java. It works with an array list, it works with a tree set, and it's a very slick and very convenient way to solve the problem of visiting each item in a collection of things. Okay, so that is the Java tree set class. So let me pause here and ask if anybody has any questions about anything that I've just said about the tree set class. Okay, now the next class we're going to talk about is a variant on the tree set. This is the next example we're going to look at is a thing called a tree map. Right now, to explain what a tree map is, let me go back to the earlier slide that showed you what trees look like. In the case of the tree set, a tree set is a structure that's organized something like this. And of course, the main purpose of a tree set is it stores a collection of data items. And in this case, the data items that we're storing are simply stored one item per node in each of the nodes that make up this structure. Okay, now the next class we're going to look at is a thing called a map. And the only difference between a set and a map is that a map stores two items in each node instead of one. And in the case of a map, the two items that are stored in each node, the first of these items is what's known as a key, and the second item is what's known as a value. Right? And the primary purpose of a tree map is to allow you to search for things based on these keys and find the values that are stored along with those keys in each of the elements. All right, and so here are the three key methods in a tree map class. The first of these, which is used to add new pairs to the collection, is called the put method. And the way it works is you give it a combination of a key and a value. It will then create a new node somewhere in the structure and store both that key and that value within that node. All right, then the second method is a method which is designed to search for things, and it works based on keys. You give it a key that you're searching for, and it will quickly search through the structure and answer the question, either does this key appear somewhere in the structure or does it not? And it will return true or false to you to answer that question. And again, since the keys and values are stored in a tree structure, and a tree structure is very fast and efficient for searching for things, the tree map will be able to answer this contains question very quickly and very efficiently. All right, and finally, the third important method in the tree map is the get method. The way that the get method works is you pass it a key that you're looking for. It will then find the entry that is associated with that key, and then in that entry there will be a value that goes along with that key, and it will then return that value to you. All right, and that is the main thing that maps are designed to do. Okay, now here's some examples of how you would typically use a map. For example, in this example, we are setting up a map that uses keys that are strings and values that are integers. And what's going on in this example is that the strings are basically going to be sort of text names for numbers, and the values that are stored along with them are the integer equivalents of each of those names. All right, so here in the first line, we set up a tree map that uses strings for keys and integers for values, and then we use the add method to add a couple of entries. Oops, sorry, just made a mistake there. That's not the tree map does not use an add method. Instead, it uses a put method. That these two should be puts. So for example, we would say, let's put in an entry that maps the word 1 to the number 1, and let's put in another entry that maps the word 13 to the number 13. All right, and then to demonstrate that you can use an iterator with a tree map in much the same way that you would use an iterator with a set, here's an example showing you how to use an iterator. Right now, one small difference when you're using an iterator with a map is that maps are capable of storing two things. They store both keys and values. And when you're iterating over the things in a map, you have to specify whether you would like to iterate over the keys or the values. Right? And the way you do that is by using a syntax that looks something like this. In this case, the first thing we're doing is we're going to the tree map and saying, I would like to work with your values. That's what this method does. And then you go to the collection of values and say, I would like an iterator that I could use to iterate over all the values that are stored in the map. All right, and then once you have the iterator, you can use the same sort of structure that we saw in the last example to write a loop that visits each one of the values stored within the map. All right, and by simply changing this part from values to keys, you could instead set up an iterator that iterates over all of the keys that are stored in the map instead. Okay, so that's a quick word about the Java map class. Okay, now the last thing that I brought along for you today is a couple of example programs that will show you how you can use some of the classes that we've been talking about today. And both of these examples are programs that I've shown in earlier examples, and in both of the earlier examples, we used array lists or arrays to do what needed to be done. What I'm going to show you now is those same examples with the array lists replaced with a more suitable class for what we're trying to do. All right, and the first example we're going to go back and take a look at is the produce tracker example that I showed in a lecture several lectures back. And in that produce tracker, we had an inventory class, which is used to store an inventory of all of the produce items that are in the warehouse. And in the original version of this program, the inventory class made use of an array list to store all of the items that were in our stock. Right now, along with that array list, I also had to write a couple of helper methods to do common operations. One of these was a find method, and the other was an exist method that we would use to either search for items or answer questions about whether or not items are available in our stock. And in the first version of this program, because the stock information was stored in an array list, to do both the find method and the exist method, we had to write loops. And that's about the only reasonable way to carry out those operations in the case of an array list. Now, the main change in this version of the program is I have replaced the array list with a tree map, because the tree map is a much more convenient data structure to use in cases where you're frequently looking things up by their names, which is exactly what's going on here. Right? So in this case, if we want to store a bunch of produce items, the more efficient way to store them is to put them in a tree map where we use the names of the items as the keys and the items themselves as the values that go along with those keys. All right? And once you switch from using an array list to using a tree map to store your items, you then get to take advantage of the fact that the tree map class is much more efficient at doing searching type tasks. Right? So for example, here's the find method where we give somebody the name of a produce item and we'd like to find the corresponding object that represents our stock of that item. All right, well here we're going to take advantage of the fact that the tree map class has a handy get method that will allow you to pass it the name of some item that you're searching for, and it will very quickly search through the structure and determine if there is an item with that key. And if there is, it will find that object and return its corresponding value to you. And that search is very fast and very efficient. Right? So that allows us to speed up the find operation, which again makes many of the things that we need to do much faster. Right? And likewise, we can also speed up the exists operation because the tree map class has a handy contains key method where you can pass it the value of some key that you're searching for, and it will do a very quick search in the tree looking for the item with that key, and it will tell you either yes or no, either yes, that item exists, or no, it does not. And again, because that search is so fast and so efficient, that makes this a much better data structure to use for this particular application. All right, so that is the produce tracker example rewritten to do things using a tree map. All right, and then a second example that I brought along is an example that goes back to a lab that we did some time ago. That was the Are These Two Lists the Same lab. And in that lab, what we were doing is we were storing data in arrays, and we were writing some code to answer questions about whether or not items appear within arrays. Right. Well, this is another example where replacing the array with a more suitable data structure would make a lot more sense. Right. So in this example, what I'm going to be doing is I'm going to be reading the two lists of numbers from their files. And then what I'm going to be doing is adding each individual lists of numbers to a set. Right. Because sets make it much faster and easier to search for things. Putting our two lists into two sets is going to be a much more efficient way to answer the question that we have to answer here. All right, so we open the first file, we go ahead and create a set that will receive the elements of that first file. We read all of the items from that first set, from that first file, and put them in the first set. And then we do essentially the same thing with the second file. We open up the second file, we create a second set, and we put the numbers from the second file into the second set. All right, now with our numbers stored in sets, it now becomes much faster and easier to answer the question, are these two sets the same? All right, the first thing we do is we use the size method to make sure that the sizes of the two sets are the same. And if they're different, we can tell immediately without doing any further work that these two collections of numbers are different. So first thing to do is just to do a quick check on the sizes, and if the sizes are different, we just print a message saying, no, these two lists are not the same, and that's the end of everything that we have to do. Okay, now in the case where the two lists of numbers have the same size, we have some more work to do. And again, in this case, the set will help us do that work much more quickly. All right, so what we're going to do now is set up an iteration that's going to iterate over one of the two sets. So then we set up a loop that visits each item in the first set. And for each item we come to, we get that next available item from the iterator. And then by using the contains method, we can very quickly go to the second set and ask, do you contain this number? And if we ever find an instance where there is a number from the first set that does not appear in the second set, we can immediately say, aha, these two lists are not the same. There's a case where there's a difference between the two lists. We can then flip this Boolean over to false. We can break out of the loop. Because we have now finished our work as soon as we find one difference between these two sets. Now, on the other hand, if we make it all the way across the first set without having found anybody who doesn't appear in the second set, that's our way of knowing that the two sets are the same. And in that case, we'll print a message saying that the two sets are the same. All right, and the key step that we need to do here, which is the set of looking in the second set and answering the question quickly, does this number appear in that set or does it not? This is something that the TreeSet class is engineered to do very quickly and very efficiently. So this will allow us to solve this problem very quickly and very efficiently. Okay, so there you have it. There we now have two new classes that we can work with whenever the need comes up for either of these. We now have access to the TreeSet class and the TreeMap class. And in future examples, if we need to make use of any of these new classes, we'll now have these things that are at our disposal, and we'll be able to make use of them whenever we need them in the future. Okay, now there's going to be a little bit of a lag because the next example that we come across where we actually will need to use either a set or a map, that won't happen until next week. But sometime next week, we'll start encountering examples where it will make sense to start using these new classes that I've introduced today. Okay, and as previously announced, what's going to be happening for the remainder of this week is that on Wednesday, I'm going to be introducing you to a problem. And then on Thursday in the lab exercise, you folks are going to basically build out this problem for me. And then on Friday, I'll be showing my solution to the problem that we're talking about. Okay, so until then, if you haven't done so already, tomorrow's election day, so please go out and vote if you haven't voted already. And I'll see everybody back again for the lecture on Wednesday.